last lab we were doing was lab 8, and lab 8 was related to standing waves in a tube. And I know for a fact that probably you did not start with it yet. That's why probably you have no questions. I also heard from other students, especially the Monday section, لأنه they did not have class and they took the recorded session of a Tuesday section. They had some difficulty, so I had to go over the material a bit for them. What about you? Did you manage, or you didn't have the time to start yet? Probably you did not start yet, right? Anyway, if you have any question, please let me know. I'm willing to meet with you if needed, okay? Yeah, because you're not asking a lot and you deserve a lot of time from me if you need. Coefficient of linear expansion is the first, is it the first? Yes, it's the first lab we take in the heat section of our physics lab. And we're gonna have the next one, lab 10, about the what do we call it? The specific heat capacity of 3 different items that we need to study. This is also heat related, okay? So linear expansion, this is the outline I would want to follow. What is linear expansion in general? How to calculate the coefficient of linear expansion, calculate or measure indirectly, like what do you need to measure to be able to find it? What is our setup? How does it function? And you will see the physics is easy, the procedure is easy, the setup is easy to understand, and the lab report is so tiny. Coefficient of volume expansion, we need to discuss a bit. How can I start from linear expansion and move on to volume expansion? You tell me, what is linear expansion in general? What can you recall, or what can you guess, or anything? Yes, linear expansion. Anything. What is linear expansion? Due to what? What does it do? What happens? Who undergoes linear expansion? I'm all ears. Am I disconnected? All right. I'm gonna write change in shape. Change in shape. I'm gonna, yes, per volume, change in volume, obviously, because I have linear expansion, so I assume in any direction, and therefore the volume, yes, so
maybe due to the vibration of the particles.
Happens due to heat, or somebody's telling me that it's also happens due to the micro vibration of vibrations of the particles. Ya Allah, my keyboard is not well. Of particles, I think I need to clean it. I don't know how though. Okay, what else? So vibration of particles, and this is basically due to heat. You see the double space I always have, and change in volume, change in shape, anything related to the material. Can I assume some material would expand, some not, some less, some more? Can you think of some material that will have some exception? Instead of expanding, they will actually decrease in size. All right, so you can think of some metal. Why did you say metal banding? How banding has to do with it? Metal banding. So you believe due to the extension of one side, probably you will have banding? Yeah, why not? I totally understand what you mean. What else? Would you like to add something? Water is an exception? I don't know. You tell me about it. Water, question mark. What about it? I would love to hear that.
I'm not sure, يعني. I thought maybe إذا you heat it, it will... لا بالعكس ما بعرف.
But why did you think of water? That's interesting. Do you think the same thing would happen for oil, or is it only water? You mean liquids or water?
I thought بالاevaporation, but I don't know.
Okay, did you read it somewhere? Did you read anything about it, but you can't remember? All right.
No.
I'm so surprised because on my interesting facts about water, and I actually did not include that in my outline on purpose. So it's outside the scope of our lab, but I wanted to talk a bit about water. Thank you, Clara. What you just said is mind blowing. Even if you can't remember or you cannot put it into words, it's okay. So what is linear expansion? So basically you said most of it. It's any solid. I'm going to start with solid and then talk about gases later. Any solid would expand due to heat, and basically heat will affect if you go down on the microscopic level, the temperature is related to the RMS, or the average speed of the particles. I'm talking about a vibration of the particles, and definitely the object will increase in length. It is actually visible if we're talking about rails, like very long rails, like this one. Thermal expansion joints like these in a certain bridge in New Zealand allow bridges to change length without buckling. So we actually are scared that whenever the changes happens, you can destroy or modify the bridge a bit, and it will actually play around with safety. So this is a very nice joints made specially for to take into account thermal expansion between different seasons. I can think that some continents, you have a very big change in temperature. We're talking beyond 40 degrees. You know this, especially if you are away from oceans or seas, and if you are on a very dry land. I'm talking plus 20 degrees, minus 20 degrees. That's a difference of 40 degrees. It's crazy. Like, it's gonna affect everything around it. I'm not talking a human behavior, human bodies and ecosystem. I'm just talking about linear expansion of stuff. So imagine you're gonna take everything into account. It's really crazy. Now, what is the coefficient? By the way, I talked solids. What about gases? Gases and liquids, they do actually expand, but we don't usually talk about linear, we talk about volume. So, but yeah, you can think of, I don't know, alcohol in a tube, in a thermometer tube, and you can think of linear expansion if you want to, because the tube is very thin. But usually liquids and gases are in a certain container of a certain volume. Coefficient of linear expansion, it's called alpha. How do we measure alpha, or how do we calculate alpha? It's basically the relative change in length divided by the temperature change, or the temperature drop, or the temperature increase. All right, so it is the relative length, the relative change in length, which means you need to relate the change in length to the actual length. All right. And yeah, delta T is the change in temperature, delta L is change in length, L is the initial length, and alpha L, if you think about it, will have a unit of, can you guess what is the unit of alpha? Yeah, give it a try. Could it be, I don't know, centimeter to the -1? Could it be unitless? Could it be, I don't know, degree C? What is the unit of alpha? Meters over degree C. Not true. Another, I'll give you another chance. Unit for alpha. Where are the boys?
1 over degrees Celsius.
Okay, you can say that, and you can also say 1 over Kelvin. I just need you to remember that the change in temperature Kelvin or change in temperature degree C is the same, because the jump is the same for Kelvin or degree C. So if we're talking delta T and not T, you can use Kelvin is equal to degree C, okay? And in some resources you will see 1 over K, and in some other resources you will see 1 over degree C. I wanted to show you something interesting in this table. 3 things I would like to discuss. Which solid has the greatest coefficient of linear expansion? And since the coefficient is proportional to delta L, I will assume which solid would expand more due to heat. Can you have a look so you can compare a bit those metals that you have around you in your houses, in your kitchen, I don't know, in your classes. Probably your classes right now are your bedrooms or your living rooms. In my case, it's my kitchen. So, which solid, according to the table, I don't know if you can see it well, expands the most due to heat? Anyone? Yes, obviously, lead is the one that is expanding the most according to the list that I have. And which one expand the least? Probably quartz, right? And which is next? Invar, which is nickel iron alloy. Nickel iron alloy. Can we have something around us? I'm just thinking about something around us. Glass. Glass is interesting. Glass does not expand a lot, obviously. I can think of marble as well. Yeah, probably. So think about these. So this is the first thing I want you to notice. Compare a bit. Two, I want you to notice that thermal expansion coefficients, those values are only at 20 degrees C, and I found this very interesting and confusing at the same time. How is alpha temperature dependent? Isn't alpha telling me what happens to my solid when the temperature increases? So temperature cannot be constant. Have some time to think about it. By the way, alpha will change according to temperature, but it will change a bit. Like it's not gonna be really different for higher temperatures, slightly different. I also want you to notice a third idea, coefficient of linear expansion versus coefficient of volume expansion. And I want to keep that for you for later on because there's a question in the lab report about this. Okay, so keep it for you. Now our job is to take a rod of a certain length we can measure with a regular ruler. Delta L can be measured not with a regular ruler because delta L will be so tiny. You need a special device to measure delta L, something like a micrometer or a dial gauge, something really sensitive to an extension of a fraction of a millimeter. Delta T can be measured so easily with a thermometer before after, or we're gonna do it with a thermostat. And by thermostat, I mean it's a resistor, the resistance of which is temperature dependent. So if I know the resistance of the resistor, I can tell the temperature. The reason I'm using a thermostat is because I need to measure the temperature of the rod, and the rod is solid. And by touching the rod with a thermometer is not enough. You know, thermometers are good to measure the temperature of the environment, to measure the temperature of a liquid. But to measure the temperature of a solid, and thus it's not really precise unless the solid is in a liquid and they are at thermal equilibrium, you know, like you have water boiling and solid inside, and you wait a bit, thermal equilibrium will happen, so you will assume solid and liquid will have the same temperature. Otherwise you cannot use a thermometer to measure the temperature of, I don't know, the surface of my phone. It's not precise at all. So we're gonna use a thermostat, and I'm gonna explain later. That's our setup. So what do we have? First of all, we have a steam generator. The steam generator is basically a container under which you have a resistance to heat, a regular resistor. So you can put it on off, and you can increase the heat from 0 to maximum. I think you have up to 9, you know, 9 different levels. And this container, it's closed, it's tightly closed. You can open it and close it. You will see in the video in a moment. I have the video still on my desktop, so we don't need to download. The container has a lid, and the lid is a tight lid, and it has 2 openings. So you can collect the steam from the first opening and from the second opening. And if you don't want 2 openings, you're supposed to close one of those by simply using a closed tube, and it's not a big deal. So I'm gonna use 2 tubes, 1 tube to collect the steam, and probably let me get a pen. So this to collect the steam, and this one I'm gonna turn it like this and clip it just to close the other tube. Now what do I have here? I have 3 rods, you can see them here. The white one is aluminum, the red is copper, and the yellow is gonna be brass. So keep in mind, white is always aluminum, and you can feel it. It's so light and so white. The red is always copper in most of the cases. So usually the remaining is tin or brass or anything on the list. You can see that each rod has a foam cover, and the foam cover is basically for many reasons. Reason number one is to be able to hold it safely. Otherwise, if it's really hot, you can burn your skin. Reason number two, under it, you have the thermistor. You want to isolate the thermistor from the environment, and also you want to keep it safe because, trust me, we had thermistors back then on some equipment that are very similar from Pasco also. And every time the students would touch the thermistor or the cable, they used to ruin them. Like the cable is used to get dislocated, and I thought those students were violent until I dislocated one myself, and I realized it was not user friendly. And you barely touch it, تنقطش. So I would say one, the reason is to keep the rod, to be able to handle the rod and not burn your skin. Two, to keep the thermistor well isolated because you want the temperature of the rod without the environment. And three, probably not to handle the thermistor and damage the thermistor. What I have here is a dial gauge. The dial gauge is something that measures the extension in length, or it measures anything. You can read what's written on it before and after and find the extension, or you can simply zero it when you're ready and find the measurement later on. It could be digital, it could be analog, it doesn't matter. Usually you put it on something. In our case, we're gonna make sure it's touching the ring. And you see this ring, white ring, and every time the rod increases in length, the ring is gonna move with it, and the dial gauge that is touching the ring is gonna write or I don't know, measure how far the ring has moved. Also, you have a tube here. This tube is gonna be used to collect the steam and to throw the steam inside the rod I'm working with. By the way, don't forget to measure the length of the rod before the experiment. And usually I always forget to do this. So I have to do it after the experiment. And sometimes the rods are too hot to handle. Some of the students would say we cannot measure the length of the rod if it's too hot because we would be measuring L plus delta L, which is true. However, delta L is very small and negligible. You cannot see it in a regular ruler. But sometimes it's above 1 millimeter and probably it's going to affect your L. So always measure before the experiment. Are the rods same in length? I don't know. I always ask the students to measure each because who knows, they could be a bit different. This is another picture of the setup. You can see the dial gauge. You can see the rod, probably that's brass. You can see an ohm meter. This is a multimeter on the mode ohms connected to the plugs in here that are connected to the thermistor. You can see the steam generator. One tube is to close. I love this. And some other tube is to collect the steam inside the rod. By the way, you will have steam going out from the other side. And this steam is very dangerous. It could be dangerous, not really dangerous, because it could go on your partner, it could go on your phone, on the screen of your laptop, and sometimes it may condensate into boiling water droplets. And this is not nice because water is going to go on your desk and you can have papers there. So always be careful on the other side of the tube. Sometimes we use a container to collect the dripping water. I was surprised to see with those new setup, new equipment, that no water has been dropping, only steam going out, and that's nice. And it makes me realize that for the previous setup, it was condensation was happening probably because the rod was not heating up in a uniform way. So probably by the end of the rod that is still cold, that's where condensation was happening. So the fact that condensation is not happening shows that probably the rod, all of it is well heated, and that's a good sign. This shows by the way, I think this is a picture from the movie, from the video. It shows the dial gauge. These are new dial gauges that we got. The previous one was analog, and it was difficult to zero and not worth it. We used to just to take the measurement before and after and find the difference because it takes you forever to zero, and then if you touch it you lose the zero. So how about not zero it, just take it randomly and measure the increase and not the length. By the way, this one measures in inches or millimeter. You pick on off button. And then you zero it when you're ready to start the experiment, because when you build your setup, you're gonna touch it and it's gonna destroy your zero. When you're ready and not touching your setup anymore, you can click on zero. And this is what I'm gonna do in the video. What else? This is another picture of the setup. What's interesting is the thermistor. When you read the value given by the thermistor or the resistance of the thermistor, you cannot tell the temperature. There's no equation. You simply have a chart. For instance, this is 10.66. 10.66 is between those two values, right? Kilo ohms, by the way. Kilo ohms means 1,000. Between those two values, it means that the temperature is between those two values. What's the smallest subdivision in temperature? It's 1 degree divided by 2 is 0.5, which means I can give up to 1 decimal. So look, 6 is closer to 450, or is it in the middle? Anyway, you can say 23.5, you can say 23.7, but don't go and say 23.85. Don't give 2 decimals. It doesn't make sense because the chart is not very precise. How can you come up with very precise measurements yourself? All right. By the way, with the list of results, I'm going to give you better values. If I can see the results, I found a beautiful results. Do you see results? Those screenshots are gonna go. This is daily screenshots. Yeah. So I found, by the way, this is just a second. It's opening. Yeah, these are the measurements that I'm gonna communicate with you. As you can see, we have brass and steel. I have no results for aluminum. I'm so sorry. So just skip the aluminum, and I have 3 trials of each. I remember back in the days, I asked the students to do only 2 rods, and I told them, let's do 3 trials of each because it's more precise, and because it was time consuming, we can skip aluminum. This is what I told them. And probably I had so many students and I didn't have enough rods. So 2 rods per bench was enough for us. And it was really time consuming, 6 measurements to do. Imagine you waiting for water to boil. You know, it's time consuming. And this is the chart that you can use. This chart is from Pasco, like the same exact chart I had on my bench. Because on one side, you can see the temperature from -10 to 45. And on the other side, you can see from 46 up to 100, because you're interested in room temperature, your initial, and on a temperature close to 100 when steam starts getting collected. All right. Anyway, I'm going to communicate this with you this evening if you want to take a screenshot because you can't wait. But Imad is not here, and usually Imad is the one who cannot wait. Yeah, and I totally feel him. More about the setup. This is a screenshot from the video that shows you temperature versus resistance for the thermistor. You can notice if it's a linear relationship or not. Think about it. You can also notice that as the resistance decreases, the temperature increases, and that's really interesting. All right. Any questions before I move on? Yes. Listen, you're not too many, so you should speak for the whole class. We're talking about 7 students. So كل واحد منكم لازم يحكي 5 مرات for you to sound like a regular class. 5 times per second. So do you guys have any question? All right. That's good. I can see the boys are very active today. Yeah. All right, lab reports, how does it look like? So as you can see, the results I gave you are a little bit different. You have the length, and that's the initial length that I took prior to the experiment, copper, brass, aluminum. This is RM, and what I mean by sub RM is room temperature. Okay, and the room temperature, when you measure the resistance, you can tell what the temperature is. So this is temperature of the room temperature. Okay, and please ignore 0 degrees C. It's actually the unit degree C. I did not see it and I did not modify it in the lab report, but you can do that on your own. Just remove the 0. I modified all the lab reports, but this one I did not see. All right, thank you so much, Gael, for the feedback. So delta L will be measured directly from the dial gauge. By the way, the dial gauge is in millimeter, and what you can read on the screen, you can see the unit on the screen, very easy to handle. R hot means this is the resistance after the rod has been heated, and we usually wait for the rod to be hot until the temperature stabilizes, and it cannot get hotter than this. Temperature hot can actually be found from the chart, and temperature room temperature will be found from our room temperature. And delta T is basically the difference between T hot and T room temperature. So if you have all that, then you will be asked to measure, to calculate alpha. You can find alpha from the values, or you can find it from any online chart and you can compare. And I don't think you need to do any other calculation but RMS if you have many trials, like average and RMS, and propagation of error to find alpha if needed, and so on. Read the question and think about it. This is a section about the volume expansion. You can see that the expansion will happen on all the three sides. And I love this diagram because it can show that you have an extension on the y-axis, extension on the x-axis, extension on the z-axis. And that's why you have an increase in volume, because you will be asked to derive the coefficient of volume expansion, and you need to take into account that the extension is happening on the three levels. And don't worry, this is a conceptual question. You can find it in any book. So if you're stuck, read a bit about it and you will be fine, okay? However, it's straightforward. Now I'm gonna talk a bit about water. I'm not gonna take a lot of time because this is outside the scope of our lab. I only think personally that water is interesting. So does water expand or contract when heated? What do you think? And what do you say? Can you think of an example? And when you talk about water, think of any phase in water. It could be solid, liquid, or gas. It doesn't have to be liquid water. Can you think of an example where the volume of water actually changes due to any heat added to your system or removed from the system? Any thoughts about water? Okay, I'm gonna give you a hint. Can you think of different phases of water? Which one is denser, for example? Who floats on who? Any example, any thought related to water? I gave you a lot of hints. I gave you answers as well. Solid denser than liquid. And that's why an ice cube actually sinks in a water cup. Is that true? Is that true that solid water that is called ice cube? It is the opposite, yes. So an ice cube actually floats on water, which means an ice cube is less dense than water. By the way, the density of water is around 1000 SI unit. The density of the ice cube is around 900 SI unit, which means the ice cube is gonna float on the water. And what does it say about the volume of the ice cube if we're talking about the same quantity of water and ice cube? Which one has a bigger volume? The solid or the liquid? The cube, the ice cube, or the water itself? Exactly. So how come you cool down your water to zero and it's gonna expand into a bigger volume? Don't you find this very interesting?
Doctor, due to the intermolecular forces,
Yes, can you elaborate a bit?
like hydrogen bonds and stuff.
Exactly, because we're talking about H2O, and between each molecule of H2O and another H2O molecule, you have some bondings in between, and this will actually force the particles to be far away for some reason. Anyway, so they're talking that water has an exception, and the exception happens at 4 degrees, and I believe this chart is really great to show you that at 4 degrees, the density is the highest. And I mean by density highest, it's the smaller volume. And then as you go from 4 to 0, the volume is gonna expand. From 4 to 12, the volume is gonna expand. But here you have the smallest volume possible. So when you cool down your water to ice, it's gonna expand. And when you heat it up to a higher degree temperature, it's gonna also expand. At 4, it has the smallest volume, and this is so cool. Yeah, why 4? I don't know. And basically, probably this is what Giscard was talking, right? What Giscard meant by discussing the hydrogen bonding between the molecules. Also, a good explanation could be, since 4 degree has the highest density, this is what happens in a pond or in a lake. And so when you have on a summer day, the temperature distribution will be as such. 4 degrees C is the most dense. So water at 4 degrees C is going to be in the bottom, and anything above more temperature is going to be above. So that's why you can think about the temperature distribution of the different flow. However, in winter season, and you have ice on the surface, we're talking about 0, and you go down, the least one, the 4, is gonna be the bottom, like yeah, at the highest depth, because it's the most dense water temperature, right? This affects a lot the water flow in lakes. It affects a lot who's living in the lakes. I'm talking about the ecosystem in general. And this is very interesting. We're talking about water, and this is how water behaves. So I thought probably we can mention it a bit, and that's it. So now the video, it's coefficient of linear expansion, this one. Yeah, this is the official one. I have it on YouTube. I'm showing you here the steam generator, how to put it on and off, all the 3 different tubes. By the way, you cannot use the 3 tubes. You can only use the one that is on top, because the dial gauge, or this one, is only connected to the first one. I was so excited at the beginning. I thought I can do the experiment simultaneously, or at least one rod after the other. Apparently, I have to finish the first one, remove it, then put the second one, and I cannot. So this is only a stand for me not to lose them or forget them on some bench, just a stand. I thought probably they can have a smarter design. Anyway, so you can see here, I'm trying, I can open the container, you can see what's inside, just water, tap water, and you have 2 tubes. One tube is closed. By the way, this is an ugly way to close it, but I couldn't find the clips, the nice, sexy clips we have. And here, this is the tube. I'm gonna insert the tube in the rod, probably not now. First, I'm gonna take some measurements, explain each color, the name of each tube, what the foam cup is for, the foam the handle, the multimeter, what it does, significant figures, how many decimals, what scale do I pick, and then the chart a bit, room temperature, and so on. This is the dial gauge. I'm touching it to show you how the measurements is gonna happen, how do I put it on my bench, and how I clip it inside, put the rod on it, and then release it, and then zero it to start taking measurements whenever the rod starts increasing in size. Yes, and I put the tube. By the way, I should put the tube first, then zero the dial gauge, because touching the rod could modify the measurements I could have. I think I zeroed it again. You'll see in the video. And you see that the measurement of the multimeter did not change yet, because the tube here is still cold, meaning no steam is being collected. And then water starts boiling. Here we wait a lot, like 15 minutes for water to boil. And the tube is hot. And eventually, you see, I put a container here because I don't want water on my desk, just for safety. And I can see that the value of R is changing a bit, decreasing a bit. And I start, you see, I will have a sudden decrease. It was 10, then suddenly 7, and it's gonna drop below 0. So what's that? 1.5 kilo ohms. Dropping, when R is dropping, means the temperature is increasing. Okay, and you can see the reading on the dial gauge, but please do not take this measurement, take the measurement in the table, because the measurements given to you in the table, and here you can see some water vapor going out. Stand in this position. So if you love your partner, don't let her stay here. All right, so by the way, we love this experiment in the winter because it's really nice to be seated around boiling water, waiting for it. to heat your system. Yeah, especially if some other benches are doing optics and it's all dark. Romantic in the physics lab, go figure. Okay, so this is the chart again to see the temperature at the end. It's gonna be very close to 90 something because it's steam, you know, it's gonna heat up your rod very high temperature, I mean. All right, and then I wait for everything to stabilize, like delta L will not, no more extension, no more increase in temperature. Take the values, change the rod, put another rod, and repeat the experiment. By the way, you were asked to do 3 trials, and 3 trials means, if I have the measurements still open, 3 trials means I need to wait for the rod to cool down again to do trial 2. So the best to do trial 1 for this, for brass, put it away, do trial 1 for steel, put it away, then brass would have enough time to cool down to do another trial. And that was time consuming. Wait for the rod to cool down. If you don't want to wait for the rod to cool down, you don't have to. But be careful, the rheostat temperature will not go down to the initial value, and L will not be the same probably. Because if the brass is still hot, let's say 60 or 50 degrees, yeah, so the L is gonna be different. And I hope you can measure it with a regular ruler. I don't know. Anyway, for those trials, we waited long enough for the rheostat to go back to 11 point whatever room temperature. Okay? And since we have a rheostat, it's easy to wait to have a reference. Wait until which value? Room temperature again. Okay? And it's not difficult because the specific heat capacity of those metals is very small, which means they heat up quickly, they cool down quickly. So I'm talking about probably 5 and 10 minutes, enough time to finish the other rod and come back to the first one, and so on. Yes. Any questions? I think that's it. I can save as this PowerPoint, call it 2. 2 means your section. And please let me know if you have any question. Otherwise, you are dismissed. Any question? You guys, you're busy doing something else? Or is it that you're only slow to respond? And I totally understand both ways. You can watch the recorded session later. It's just only boring on your group, that's all. Yes, of course you can ask me, George. Yes, of course. Yeah, so I'm gonna stop sharing my screen. Bye, everyone. Yes, George. I'm here for you. Tell me.
Hi, Doctor. Sorry, I won't take a lot of your time. I just have 2 questions.
You can take all the time.
The first question is concerning the lab reports 6, I think, rotational inertia. I submitted it, but I had like a missing question which I did not know how to solve.
Okay.
So I was wondering if before correcting or something, I could join your office hour and I could maybe you could explain it to me so that I can fill them and not to lose points.
Of course. And do you think we can do it now, or do you think you need time to focus and we should do it later? You want to try us to do it now? You have.
Oh, I'm really sorry. I just entered because I thought Kenshi class. I just finished. I had a meeting with.
Yeah, they told me, Mia. They told me actually we had a class and we just finished, like now, 1 minute ago.
If.
By the way, I'm still recording. Let me close.